Hi. So in this video, I am going to discuss how to understand Newton's identities for symmetric polynomials of roots. So this was a request from one of the students, and let's get into it. So first of all, we want to figure out what is a symmetric polynomial of the roots, right? So if you have an equation like this, ax squared plus bx plus c is equal to 0, and let's say roots are alpha and beta, what is a symmetric polynomial? A symmetric polynomial will be when powers of the roots are the same. So this is an example of a symmetric polynomial. Let's call it E1 because degree of this symmetric polynomial is 1. So alpha square plus beta square will be E2. Alpha cube plus beta cube will be E3 and so on. So these are symmetric polynomials. Degree of each term is basically equal, right? So what do we do here? So what we want to find out is the sum of all the powers of the roots, right? So Newton's identities give us a recursive way to generate sum of powers of the root, sum of powers of roots. So suppose somebody asks you alpha power 4 plus beta power 4. So this thing is not very easily computable by just the Vieta's relations. We know Vieta's relations give us alpha plus beta is equal to minus b by a, and alpha beta is equal to c by a. But what else can we get from there? We can actually get it, but it might be long. And if it was alpha power 9 plus beta power 9, then there is no nice way to get this, right? So we are going to understand the way in which we use Newton's identity. So let's talk about the quadratic case, right? So we'll start off with quadratics, then we'll move on to cubics, and finally we'll do the nth degree polynomial. So if it's a quadratic equation, ax squared plus bx plus c is equal to 0, right? Let's define si as alpha power I plus beta power I. We want to figure out a way to get si, right? Alpha power I plus beta power I. So let's start off with S0. S0 is simply alpha power 0 plus beta power 0 is equal to 2. S1 is alpha plus beta is equal to minus b by a from Vieta's relation, right? Now S2 is equal to alpha square plus beta square, which can be written as alpha plus beta multiplied by alpha plus beta minus 2 alpha beta, which can be now written as, because this part is minus b by a, we can write it as minus b by a multiplied by, we can write this alpha plus beta as S1, right? So I'll write it as S1. And notice what is S2? S2 is this, right? So minus S2 into what is alpha beta? Alpha beta by Vieta's relation is C by A, right? So we get this relation minus B by A S1 minus C by A S2, right? This is equal to C by A S0. I made a mistake here. So if you think about this 2 is actually S0, right? S0 and alpha beta is C by A. So we get this relation minus B by A S1 minus C by A S0, right? Let's see if the pattern persists when you go to higher powers. So alpha cube plus beta cube, right? So now can we write this in terms of alpha square plus beta square? Yes, we can. So let's do alpha plus beta into alpha square plus beta square. And notice what you have to do. You have got alpha cube and beta cube here, but you have got extra terms like alpha square beta. So we have to subtract that. And you have also got a term alpha beta square, right? So that is basically alpha plus beta into what is alpha square plus beta square? That is clearly S2 minus alpha beta common. And this is alpha plus beta. So now I can write this as S3 is equal to alpha plus beta is minus b by a multiplied by S2 minus c by a, and alpha plus beta is my S1, right? So you're beginning to see a pattern here, right? So S1 was this, we know that already. S2 was minus B by A S1 minus C by A S0. S3 was minus B by A S2 minus C by A S1, right? And we can continue like this and say S4 should be minus B by A S3 minus C by A S2, right? S4 will be this, following this pattern here, 3, 2, 1, 4, 3, 2, right? Similarly, what we can write for a quadratic equation is Si will be equal to minus B by A Si minus 1 minus C by A Si minus 2. So this is a recursive relation that gives you the value of your powers of the roots, right? So if I had a question where, let's do a typical example for this. So let's say x square minus 3x plus 2 is my quadratic. I know the roots already. I've chosen the quadratic so that the roots are simple, 1 and 2. For a moment, forget that we know the roots, right? Let's say it were alpha and beta, right? And suppose you wanted to find alpha power 5 plus beta power 5, right? So that is equal to S5. So what I should say is minus B by A S4 minus C by A S3, right? So here putting the values here, minus B by A. So B is minus 3 and A is 1, right? So minus B is 3 and A is 1. So 3S4 minus C by A. C is 2 and A is 1. So minus 2S3, right? Now I have this relation, S5 is equal to this. So how do I find this? I need to find S4 and S3. So S4 will be similarly 3 times S3 minus 2 times S2, right? Okay. I have to further find S3. S3 should be 3 times S2 minus 2 times S1, right? And S2 was what? S2 was 3 times S1 minus 2 times. Now you have reached S0, right? S0 is also 2, right? So this is 3 times S1 minus 4. And sum of the roots here is known by Vieta's relation. Alpha plus beta is minus B by A, so 3. So this is 3 into 3 minus 4. So this should be 5. Notice that our S2 value is correct. We actually know the roots. 1 square plus 2 square is S2 is equal to 5. And that has come from the recursive relation, right? S2 has come. So now we can easily find everything because S3 will be 3 times 5 minus 2 times S1. S1 is 3. So this becomes 15 minus 6, 9. So S3 is 9 and S4 will be 3 times 9 minus 2 times 5. So 27 minus 10, 17. And S5 will be 3 times 17 minus 2 times S3, so which is 9. So 51 minus 18, so that is 33. Now you can confirm that this recursion is giving us the correct value because 1 power 5 plus 2 power 5 is actually 33, right? So we understand what to do if it is a quadratic, right? Basically, I'll just recap quickly. If it is a quadratic equation, ax squared plus bx plus c is equal to 0. You can write these Newton's identities or basically in the form of a recursion. S0 is 2, S1 is minus B by A, S2 is minus B by A, S1 minus C by A into 2, S3 is 2 is basically S0, remember, right? S3 is minus B by A, S2 minus C by A, S1, and so on. It continues this pattern. So Si will be minus B by A Si minus 1 minus C by A Si minus 2. So this we have also confirmed with an example. A similar type of relationship exists for a cubic relation, cubic equation. So let's say we have a cubic like this, ax cube plus bx square plus cx plus d is equal to 0, right? Let's say alpha 1, alpha 2, alpha 3 are the roots, right? Now, what is Vieta's relation telling us? Vieta's relations tell us that sum of the roots, alpha 1 plus alpha 2 plus alpha 3, is equal to minus b by a. Sum of the roots taken 2 at a time is equal to c by a. Sum of the roots taken 3 at a time, or basically product of the roots, is equal to minus d by a. So this is from Vieta. Now we will try to construct our polynomial, symmetric polynomial. So S0 will be alpha 1 power 0 plus alpha 2 power 0 plus alpha 3 power 0, which will be simply 3. S1 is simply alpha 1 plus alpha 2 plus alpha 3, so minus p by a. S2 will be alpha 1 square plus alpha 2 square plus alpha 3 square, which can be written as alpha 1 plus alpha 2 plus alpha 3 multiplied by alpha 1 plus alpha 2 plus alpha 3 minus 2 times alpha 1, alpha 2 plus alpha 2, alpha 3 plus alpha 3, alpha 1, right? So this part can be written as minus p by a. This part can be written as S1. And this part is basically S minus 2 times c by a. 2 times c by a, right? So this is my S2. Notice that S2 is not very easy to predict for a cubic equation, right? You have to remember that 2 comes in the second equation for S2, right? S1 is simple. S1 is simply Vieta's relation. S2 is this, right? I will do this in the next page now. So for a cubic, ax cube plus bx square plus cx plus d is equal to 0. We have S0 is 3, S1 is minus p by a, S2 is minus p by a S1 minus 2 times c by a, right? S3 you can confirm in the same way that it will become minus p by a S2 minus c by a S1 minus d by a S0. And notice that S0 is 3, right? S0 is 3. So this can also be written as S3 is equal to minus p by a S2 minus c by a S1 minus 3 times S0, 3 times d by a, minus 3 into d by a, right? So this is S3. Now S4. So S4 onwards, the formula is much more simpler. We don't have this arbitrary 3 and 2 and so on. So basically what I'm trying to show you here is that the formula for powers of roots differs in 2 cases. So if you want to find S of I, right? Correct? And your equation is nth degree. Your equation is nth degree, right? Now formula will differ in these cases when I is less than equal to n minus 1, right? The formula will follow this pattern. And when I is greater than equal to n, it is much more simpler. The recursion is very simple. You can just say I, Si is great, Si will be equal to minus b by a Si minus 1 minus c by a Si minus 2 minus d by a Si minus 3 and so on, right? Correct. I will show you this with an example actually. That will be better. Just hold on for a second. This is correct actually. This is the expression for Si here, minus d by Si minus 3. So let's think about this part, which is slightly unclear for nth degree polynomial, and how does the formula differ in more detail. So if I take an nth degree polynomial here, let's say a polynomial or Px is equal to, let's say we take a k degree polynomial. So a k x bar k plus a k minus 1 x bar k minus 1 plus a k minus 2 x bar k minus 2 and so on till a1x plus a0, right? So what am I trying to find? I'm trying to find Si, which is equal to sum of j goes from 1 to k alpha j to the power I. So why is j going from 1 to k? Because the polynomial has degree k, so their roots will be alpha 1, alpha 2, alpha 3 till alpha k. There will be at most k roots, and it is the ith power of each of them, and you're doing that sum. You want to find si, right? So let's for a moment denote these symmetric polynomials like sum of all the roots. Alpha 1 plus alpha 2 plus alpha 3 and so on till alpha k. Sum of all the roots will denote by e1. This is e1, sum of all the roots taken one at a time. This is clearly going to be minus ak minus 1 by ak. That is the Vieta relation that I'm doing. Then if you do sum of the roots taken two at a time, let's call that e2. That will be equal to ak minus 2 by ak, right? Then e3 is equal to sum of the roots taken three at a time, alpha I, alpha j, alpha k. That will be equal to minus ak minus 3 by ak, right? And similarly, I can define the ek polynomial, which will be sum of the roots taken k at a time, right? Or basically product of the roots, right? So that will be minus 1 power k a0 by ak, right? So these are my polynomials, symmetric polynomials that will come in the recursion that we develop. Just like minus b by a and c by a, these terms appeared in the previous quadratic and cubic cases. Similarly, these terms will also appear in the case for a general k degree polynomial, right? So what we will do is we'll split the k degree polynomial formula into two parts. For I less than k minus 1, so suppose you want to find si, right? You need alpha 1 power I plus alpha 2 power I plus so on plus alpha k power I, right? Now it depends on what value of I you need. Is I less than equal to n minus 1? So if my polynomial is a biquadratic or n is equal to 4, then I must be less than equal to 3. In that case, we will follow the recursion method that we have developed. So what we will do is S0 will be equal to K, because S0 is just power 0 on all the roots. So 1, 1, 1, 1, K times, right? S1 will be equal to E1 into 1. E1 was what? E1 was sum of the roots. Alpha 1 plus alpha 2 plus so on, right? Alpha K. And notice that S1 means the same thing. It is just sum of the roots, right? So S2 will be equal to E1 into S1 minus E2 into 2. Okay. S3 will be equal to E1 into S2 minus E2 into S1 plus E3 into 3. We will confirm all this with an example. So just hold on for a second. And finally, S of k minus 1, right? You have to go up till k minus 1 you can go, right? Because this formula is valid only for the case when this recursion is valid only till the case when your I is less than equal to k minus 1. So in that case, it will be simply E1 S k minus 2 minus E2 S k minus 3 plus so on. You are basically alternating the signs E1, E2, E3. You're alternating the signs and you're starting with one less than this, k minus 2, k minus 3, k minus, and so on. And at the end, you have to be a little careful. It is minus 1, k minus 3, e k minus 2, and this is S1 plus minus 1 to the power k minus 2, e k minus 1 into k minus 1. This is the k minus 1 factor that appears. Notice that this factor is always there. This 3 was here, so then this 3 is there in the last term, right? This 2 was there and this 2 is there in the last term, right? Even for the first one, this is valid. So I'm just extending this formula here. So in order to get a better grip on this, let's do an example here. So let's take a fourth degree polynomial, right? So fourth degree polynomial has roots, let's say This is my polynomial. Okay, this is a 4th degree polynomial. I will multiply it out and write it properly. So roots I already know. Roots are 0, plus minus 1, and 2, right? So keep those in mind. What is this polynomial? X into x square minus 1 into x minus 2. So this becomes x cube minus x cube minus x, and minus 2x square plus 2 and multiplied by x. So this becomes x power 4 minus 2x cube minus x square plus 2x is equal to 0. This is my polynomial. Okay. Now for this polynomial, what is my S0? S0 is equal to k. So k is what? K is basically 4, right? Because there are 4 roots for the polynomial. So actually this polynomial will be weird because of the fact that you have 0 as one of the roots, right? So S0 will not be defined properly. So we'll not take this polynomial as an example. What we can do is slightly tweak it. 1 second. So suppose x power 4 was here, right? We already know S1 actually. There is no need to worry. S1 we already know. S1 is minus minus 2, right? So S1 is 2, right? And S2, let's check whether that is coming. S2 is equal to E1 S1, E1 S1 minus E2 into 2, right? So what is S1? S1 is 2, so 2 E1 minus 2 E2, right? Now E1 is what? E1 is the symmetric polynomial taking one at a time. Sum of all the roots is E1, right? So sum of all the roots is already we know is 2. So this is 2 into 2 minus 2 into E2. E2 is roots taken 2 at a time, right? So minus B by A is this one, and plus C by A, right? So minus 1 is E2, right? So 4 minus 2 into minus 1. So 4 plus 2. S2 should be 6 for us. What is E1 and E2? We had defined on the previous page. So E1 was summation of all the roots taken one at a time. By Vieta, it is simply 2 in this relation. And E2 was what? E2 was sum of the roots taken 2 at a time. That is C by A. So it is minus 1 in this case, right? So S2 is coming 6. Let's confirm whether it is 6 actually. So our roots were 0, plus minus 1, and 2. So what is S2? S2 is square of all of these, right? So 0 square plus 1 square plus minus 1 square plus 2 square. So that is clearly 4 plus 1 plus 1, that is 6. So this is correct, right? What is S3? S3 will be equal to E1 S2. E1 was sum of the roots taken one at a time. So 2 S2 minus E2. E2 was minus 1 into S1. S1 was 2 plus E3 into 3, right? Plus E3 into 3. E3 is sum of the roots taken 3 at a time. So 3 into sum of the roots taken 3 at a time here. Minus B by A, C by A, minus D by A. So minus 2, minus 2. So you're getting S2 is 6, so 12 plus 2 minus 6. So this should come out to be 8, right? So now check the roots. Are the cubes adding up to 8? Yes, because 2 cube plus 1 cube plus minus 1 cube plus 0 cube is equal to 8, right? So again, we have verified that this is also correct, right? Now, till where will we follow this sequence of formulas? Till where will we follow it? We'll follow it till S4, right? No, we'll follow it till S3 only, because our equation was 4th degree, right? Our equation was 4th degree, so I is less than equal to k minus 1. So I is less than equal to 4 minus 1 is equal to 3. Till 3, our recursion is valid. So till S3, we have checked also all the answers. Now the question is, what happens for S4 and so on, right? So let me just write down the polynomial on the next page. X power 4 minus 2x cubed minus x squared plus 2x. 4 minus 2x cube plus x square plus 2x square. Was it plus x square? Minus x square plus 2x. Okay. X power 4 minus 2x cube minus x square plus 2x. This is my polynomial. And I want to find S4 here, right? S4 I want to find. I know the roots are 0, plus, minus 1, and 2, right? So that I will use to check later on. So I want a formula for S4, I greater than equal to k in that case, right? Because k is equal to 4 for us. K is the degree of the polynomial. K is degree of the polynomial. I is the subscript of the S. And we want to find S of I, right? Where it will be basically alpha 1 to the power I plus alpha 2 to the power I and so on, right? So if I is greater than equal to k, the recursion is very simple. The recursion is Si is equal to summation of j goes from 1 to k minus 1. This is the Newton's identity. J plus 1 E of j p I minus j. Now it Si minus j. Si minus j. Now this looks a little complicated, but actually if you write down the terms, you will get a pattern very quickly. So when j is 1, what is this? Minus 1 to the power 2 E1 Si minus 1, right? Plus minus 1 to the power j is 2 now. So 3 E2 Si minus 2 plus minus 1 to the power 4 and j is 3. So E3 Si minus 3, right? And this goes on till when j is k. So minus 1 to the power k plus 1 ek Si minus k, right? So let's simplify it a little more. You'll see a pattern. This is plus 1. So it is E1 Si minus 1 minus E2 Si minus 2 plus E3 Si minus 3 and so on till minus 1 k plus 1 ek Si minus k. So now remember what your E1, E2, E3 were. You should go back to that screen in the video where we had discussed what E1, E2 are. E1 is basically sum of all the roots taken one at a time. By Vieta, it will be minus. In this question, it will be minus of minus 2. So plus 2. E2 will be what? E2 will be sum of the roots taken 2 at a time. In this question, it will be minus b by a plus c by a. So it will be minus 1. E3 will be d by minus plus minus. So it will be minus d by a. It is sum of the roots taken 3 at a time, right? So minus d by a. So that is basically minus 2 in this question, right? Now, suppose I wanted to find S4, right? S4 fits the condition where I is equal to 4 and 4 is greater than equal to k, which is 4, right? So I have to use this result, correct? So for S4, what I will write is S4 will be equal to E1 S3. I'll write it here. S4 is equal to E1 S3 minus E2 S2 plus E3 S1. And you will go till k becomes k, right? So 4, you will go till 4. So next term is minus E4 Si minus S0, right? Right. You're going till S0 term. You have already reached E3 S1. So S of I minus k, right? Correct. So let's see what comes. This will be just 4 here. Yes, this will be just 4. Let's just confirm whether it is coming or not. So E1 is what? E1 for us is 2. S3 is what? S3, we have already found S3 in the previous step, previous screen. S3 was 2 cube. S3 was 8, right? 2 into 8 minus E2 is what for us? E2 is minus 1. S2 was what? S2 was sum of squares of all the roots. So 4 plus 6, S2 was 6. Plus E3 is minus 2. And S1 is basically sum of all the roots. Sum of all the roots is 2 minus 4e4 minus 4e4 is what? E4 is the product of the roots, right? And product of the roots, you will realize here is 0. So this part is gone. So let's see what is the calculation coming out to be. 16 plus 6, 22 minus 4. So 18, right? We are getting 18 here. And you will realize that that is 2 power 4 plus 1 power 4 plus minus 1 power 4 plus 0 power 4. That is also 18. So we have validated this formula, right? Correct. We have validated this formula for a biquadratic equation and S4, right? So what happened here? The E4 S0 is always 4, right? So remember that S0 will be equal to the degree of the polynomial, right? Because every root power 0 will give 1. So keep that in mind. By definition, it has to be 4. So after that, this is done. So I'll just summarize for a nth degree polynomial or kth degree polynomial in our case, right? So pk is equal to a power ak x power k plus ak minus 1 x power k minus 1 and so on till a1x plus a0, right? This is my polynomial. Now you should know what e1 e2 are. E1 is summation of all the roots taken one at a time, so that is minus a k minus 1 by ak. E2 is summation of all roots taken 2 at a time, that is ak minus 2 by ak. These are all Vieta's relations. And similarly, ek will be product of all the roots, right? So that will be minus 1 power k a0 by ak. So once we know this, we are able to write any SI. SI is basically alpha 1 to the power I plus alpha 2 to the power I plus so on till alpha k to the power I. We will be able to write any SI. How do we write any SI? We have two cases. One case is when I is less than equal to k minus 1. And one case is when I is greater than equal to k, right? For this I less than equal to k minus 1, you should start from the beginning. S0 will be k, S1 will be E1 into 1, S2 will be E1 S1 minus E2 into 2, S3 will be equal to E1 S2 minus E2 S1 plus E3 into 3, and so on. Sk will be E1 S of k minus 2 minus E2 S of k minus 3 plus so on till minus 1 to the power k minus 2 ek minus 1 into k minus 1. So this k minus 1 factor always comes when you are looking for small powers, when it is less than the degree, right? Degree minus 1, right? So remember, this part is the tricky part. This 3 comes here when S3 is done, 2 comes here when S2 is done. That is the k minus 1. You should always start from the beginning here. Don't start from here, then you will be confused. Start from S0, S1, S2 and slowly construct your series. Whichever number equation you are writing, S1, that number will come in the last term, 3, right? If I is greater than equal to k, the relation is very simple. You just have Si is equal to E1 Si minus 1 minus E2 Si minus 2 plus E3 Si minus 3 and so on till minus 1 to the power k plus 1 S of I minus k. This is the recursion or equation, Newton's identity for powers greater than k. So this should help you solve problems. You should check this result with a few examples. You can refer to the Brilliant website or AOPS. There are proofs for this. The proof is very straightforward. We can actually cover it. What you have to do is basically take an equation. I'll just quickly go over the proof also as well. So let's say you have an equation, polynomial like this, an xn, an minus 1, xn minus 1, and so on, an minus 2, xn minus 2, plus a1x plus a0. Let's say this is my polynomial. Now, let's say the roots of this polynomial are x1, x2, so on till xn, right? Now, because this px is this, we know that p of x1 is equal to p of x2 is equal to p of xn. All the roots will be equal to 0, right? So put all of these roots inside. Put all the roots in this. So one equation you will get is a1 x1 power n plus an minus 1 x1 power n minus 1 and so on till a1 x1 plus a0. Another equation will be an x2 power n plus an minus 1 x2 power n minus 1 plus so on a1 x2 plus a0 is equal to 0 is equal to 0. We are just substituting the roots in this equation. And lastly, last equation will be an x power xn power n plus an minus 1 x n power n minus 1 plus so on plus a1 xn plus a0 is equal to 0, right? We get these equations. What you have to do now is every equation you multiply by the corresponding root to the power k minus 1. So I'm multiplying each equation by corresponding root to the power k minus 1, k minus n, right? So what you will get here, you will realize that you will get, when you multiply by k minus n power, this power becomes k, no? You will get an, something like this, an x1 to our power k plus an minus 1, x1 to the power k minus 1, and so on, plus a1 x1 to the power k minus n plus 1 plus a0 x1 to the power k minus n is equal to 0. And you will get similar equations for each of the variables till xn k plus each of the roots. You will get basically n equations. You have to get n equations here also. Everyone will have their own root and powers are like this. So a1 xn k minus n plus 1 plus a0 xn k minus n is equal to 0. Now, if you add up vertically, right? If you add up all of these equations, there are n equations here. Like there are n equations here, right? If you add up all of them, what you will get is an common, and look at what this is. This is x1 power k plus x2 power k till xn power k. So that is simply s of k, right? This becomes an minus 1 s of k minus 1. This becomes an minus 2 s of k minus 2. And so on till you get a1 into s of k minus n plus 1. And finally, a0 s of k minus n is equal to 0. So this is another way to write your Newton's identities. So for any equation and any power, you are getting an sk plus an minus 1 sk minus 1 plus an minus 2 sk minus 2 and so on till a0 sk minus n, right? So that is why we got that relation earlier. Like we got an s, let's say s4, we'll get an minus 1 s3 plus an minus 2 s2. And if it was a fourth degree equation, you will have an minus 1 s1, right? X power 4 ax cube bx square. And one final term will be an minus 2 n minus 3 n minus 4 into s0 is equal to 0. This equation for a fourth degree equation, this identity is basically the identity that we derived for S4 in the previous screen. S4 we had written like this only. You should confirm that this is the same thing as the previous screen. This is just formulated in a slightly different way, but we are getting all the powers, all the higher powers of roots in terms of lower powers of roots, right? This is also a recursive relation, right? So you can start off with the lowest powers and then build up this relation. I will probably make another video as a follow-up for this, and where I will discuss a few problems based on Newton's identities. For now, just remember that the previous screen, the theory that we had written was correct. You should go through that in detail. Be very comfortable with doing it for a cubic and a quadratic equation. Go through the first 5-10 minutes of the video and we're doing cubics and quadratics, right? There it is far more simpler to think. When it is an nth degree thing, there are two cases. When you want S of I, you can either go for I which is greater than equal to n, or I which is less than equal to n minus 1. The formulas are slightly different for both the cases, and I have enumerated the formulas in the previous screen. So make sure that you copy them down and use them in a few problems. You will get the hang of it. It is a slightly confusing thing to understand at first, but only by doing some practice problems will you probably get it. So try it out, and I'll probably make a follow-up video with questions on Newton's identities. See you next time. I hope you got something out of this video.